In this video, we're going to take a look at some of the theoretical concepts we saw in the previous one, but in practice. These sessions are totally optional. Feel free to skip them if you're not too much into coding. However, I thought it could be quite fun to see how all of this translates into practice. So to start with, I wanted to show you what a multi-layer perceptron actually looks like when you try and implement it. And we're going to start from one layer of the perceptron. We saw that this can actually be implemented as a series of matrix operations. You will recall this picture from last video. Now, to implement this, first of all, we're going to import NumPy. This is kind of a Swiss Army knife library for mathematical operations in Python. And now we're going to implement this layer of the MLP. You will recall that this layer has got 3 neurons. So the weight matrix has got 1 row per neuron, and each neuron has got 2 inputs. So the weight matrix has got 2 columns to hold the 2 weights associated to that particular input. And that's how we can very simply implement that matrix using NumPy arrays. And we are also going to implement the input vector. Now we're going to start with a 2x1 vector. If you remember, we saw that you can take the input and add a batch dimension and have a lot of inputs go through the MLP all at the same time. But here, for simplicity, we are going to start with just one input. And a little thing that you will see is that in the example I did here, we've got 0.1 and 0.2 as inputs, but I thought it would be better to have 0.15 and 0.25 because this allows us to have a better looking output for this. So let's do that. And we've now implemented the weight matrix and the input. And to perform the forward pass, we can simply take the matmul function, which performs the matrix multiplication, and take the weight matrix and multiply it by the input. And that gives us the output vector. And the column, the first column and the only column in this case, is the output for the first data point. Now, if I wanted to add more inputs to this batch, I would add more columns to the input vector, as you see here. So 0.3, 0.4, and so on. And obviously I can do, and that's the advantage, I can do exactly the same matrix operation. And there you have it. Now in the output, I have each column matching or being the weighted sum of those neurons for each and every of these inputs. Before moving on, I actually want to show you how to reshape this input vector into something that makes a little bit more sense. And if you use any deep learning library in the world, they will probably shape the input tensor as I'm going to show you now. So here in my version, I have the first dimension as the number of features and the second dimension as the number of inputs in the batch. So you can see here the first one, the second one, and the third one. This is not very, this works, but it is not the most straightforward way of doing it. Instead, the majority of deep learning libraries will have the input like this. The first dimension is going to be the batch size, and the second dimension is going to be the number of features of that particular problem. So you can see how I have simply modified this into this, and now each row is a single data point or a single sample, and each column is the feature of that particular sample. So we can implement these or instantiate these. Calling shape shows us that actually the shape of these is 3 by 2. And then we can want to show you that if we try the matrix multiplication that we did before between the weight matrix and this new input, that is going to error out. The reason for this is because there is a mismatch in the dimensions of the matrices. Obviously, the row by column multiplication requires that there is a matching number of rows and columns between the first and the second one, otherwise it can't be performed. So to fix this, I'm just going to comment this because I don't want it to error out. To fix this, we have various options, but what libraries typically do, they take the weight matrix and they transpose it before doing the forward pass. So a transposition simply means taking the original matrix, rows and columns, and simply, again, literally transposing that. So now the weight matrix looks like this. So each column is represents a single neuron, and the rows represent the number of inputs of those neurons. And now we can perform the matrix multiplication in probably a much more intuitive way, taking the input vector and the transposed weight matrix. By the way, the way I transpose this, I didn't say, is by calling t, which is a capital T, which is a function that NumPy gives you to quickly transpose a matrix. So if I do the forward pass, there we have it. And obviously, this also changes the shape of the output. Now the first row actually corresponds to the first input. So this is the weighted sum for each of those neurons of the values of this input and so on. So you can see that it's the previous example I had, the columns were actually the outputs. The columns corresponded to each element in the batch. Okay, so now we can very quickly also add a bias term. This is something else that, to simplify the previous video, I simply skipped most of the times. There is obviously a bias. We've got 3 neurons in this layer, so we've got a vector with 3 floating point values, which are the biases. I am instantiating that vector of biases here, and I'm doing the standard forward pass and then adding the bias. Very simple, especially with libraries like NumPy. You can add this bias, which is a single row, to each and every of these just by using the plus sign. Very simple. We also saw that we typically want to apply activation functions at the output of each neuron, and these adds typically non-linearity, and we saw how important that is to actually build powerful MLPs. And here I just wanted to quickly show you how to implement one of the most popular activation functions, which is the rectified linear unit, or ReLU. And obviously it's just a line of code, couldn't be simpler. So here I'm defining the function, then I'm doing the forward pass, and I'm simply applying the ReLU. And as you can see, obviously what the ReLU has done here has taken all of the negative values that we had and has turned them into 0, and it hasn't touched the other ones. So for the second part of this, I want to show you how this is implemented in PyTorch. PyTorch is simply one of the most widespread deep learning libraries. There is another one called TensorFlow by Google, but for all intents and purposes, PyTorch today is the one that you're going to see most used in the majority of projects. So to use it, it's very simple. We import Torch, and then from Torch, we also import NN, which stands for neural networks. And then we can go in and actually instantiate what's called a linear layer. Now, a linear layer is exactly one layer of a multi-layer perceptron. So if you look at this layer, it's got 2 input features and 3 neurons, and that would be a linear layer with 2 input features, that's the first argument, and 3 neurons. We just do that, it's implemented, and then we can go and look, if we wanted, at the weights, and inside this layer you actually see the weight matrix as we saw before. That's identical to what we had there, and you will see that every time you instantiate this, if I instantiate a new one, PyTorch will initialize this with a set of small random weights. Incidentally, there is also a bias array that we saw before. Now, I wanted to show you with this example that what we did before manually with PyTorch is actually, with NumPy, is actually the same as PyTorch was doing or is doing. And to do that, I am going to override these random weights and biases by actually setting them to the values that we had in the previous example. So here I'm setting the weights for the weight matrix, and here I'm setting the bias. So now I can create an input tensor. You see that before we created a NumPy array to contain the input. PyTorch works with something similar, which is called a tensor, as we saw before, which is just a generalization of a multidimensional array. So if I go here, this is exactly, ultimately the same input tensor. And now, to perform the forward pass, instead of manually doing the matrix multiplication, I can simply take this layer, take the input tensor, and pass it to that particular layer, and that's the output. You will see that this matches exactly, or should match exactly what we got here, which indeed, if you check, it does. Finally, I also want to add the activation function, so I can import from the functional module in PyTorch the ReLU function, which I can use. So again, I'm going to do the forward pass, store everything in the x variable, and then I'm going to take the x variable and pass it through the ReLU function. And exactly as you're expecting, no surprise here, everything which was negative has become a 0. All right, we are actually ready to implement our first multi-layer perceptron to perform a real task. Here we're going to be using the MNIST dataset, which is essentially a collection of 28 by 28 grayscale images of handwritten digits. This is often considered the Hello World dataset for machine learning. Now, the first thing to do is to get that dataset and take a look at it. So this cell is going to download the dataset and extract it inside our Colab notebook. And we can go here and see that we have now a folder called MNIST, which contains 2 subfolders, training and testing. And the training folder, you can see it contains 1 digit or 1 folder per digit. And if we open one of these, we'll see that it contains the actual images of the digits that we can use to train the network. I'm going to open a couple, and you can see that some of them are quite different, and there are quite a lot of samples in here. Now, we want to load this into our notebook. Let me just close all of these, and we want to process the images using a library called peel from Python. So let me just first import that. And if I provide the path to one of those images, actually the first image that we saw, we can open the image and display it. So this simply allows us to load the image in memory. As we saw, we now want to take that image and transform it into something that the neural network can understand, which is a set of input features, and in this case the input features are just going to be the grayscale values of each of the 28 by 28 pixels that we have in this image. So to do that, we have the image that we have read, that's just a PNG, and we're going to use some transforms from PyTorch that make this particularly simple, so that from the image we obtain a tensor. Let's run this, and you can see that the tensor, the shape of that particular tensor is 28 by 28, which is exactly what we're expecting here. And I can also print that tensor, and you will see that now each of these rows corresponds to a row in the image. And then you can see, for example, 1, there is a lot of 1 because obviously the 1 represents the color white. But if you go down there, you see other grayscale values which represent the number drawings here. And we can also very easily access individual pixels just like that. So for example, this pixel here has the value 1 because it's blank. One thing that might be actually quite useful to show you now is how to use the matplotlib library to show one of these tensors as an image. I've got here a method, and I can pass the tensor image to that image show method, and there it is. We can easily take a look at that as an image, because obviously taking a look at a tensor it's not really easy to recognize which numbers we are looking at. So the next step, the most exciting part, hopefully, of this session is that we are now going to create a multi-layer perceptron for the problem of recognizing these handwritten digits. Here I have the generic image from a multi-layer perceptron that I showed you in the previous video. Obviously, the number of input features in the input layer, the output layer, we need to change all of that. Let's take a look at how this is implemented. It's actually quite simple. First of all, we define our MLP as a class in Python, and this class will extend the module class from the PyTorch NN or neural network module. Now, in the constructor, we can create the layers that we want, so we can assign the properties. This could be called anything. I'm just calling them layer 1, 2, and 3 for simplicity. And now, the first layer is gonna take the input features. So we have 28 by 28. So this is gonna be the input number of features, and then it's going to output 100 activations, which means it's going to go into a next layer with 100 neurons. Then the next layer is going to take the 100 outputs, and it's going to have 150 neurons in there, and these 150 neurons are then going to go into the last layer, which is going to output 10 outputs. Now remember that what's really fixed in this problem is this value here, because that's the number of input features, the number of pixels, and this value here, because this is a multi-class classification problem, which means that we want 1 neuron per class, and each of these neurons is going to essentially output the probability that the input corresponds or belongs to that particular class. So 10 digits, 0, 1, 2, 3, up to 9. The rest we can change. We could add additional layers, we could change the shape of these layers, but obviously if this is 101, this will need to match that and be 101, because we have to fully connect these layers to each other. Now, this is just the essentially definition of the layers, which inside have got the weight matrices and the biases. And we also have to implement the forward pass, which is particularly simple here because we're going to take the input X and pass it through the first layer and then pass it through the ReLU activation. Then we're going to take this and pass it to the second layer into the ReLU activation. And finally, we're going to take that and pass it to the third layer and return it as the output of this computation. One thing to notice is that the last layer, we are not applying a activation function. There is no ReLU, softmax or anything like that. And this is because for multi-class classification problems, we typically want our network to simply output some logits, so some raw scores, which we can then later on pass to something like softmax, as we will see, to get the probability distribution. Now, let's instantiate that class. I think I haven't done this. Okay, so now we've instantiated the model, and the nice thing is that now PyTorch is going to keep track of all of the weights and biases and all of the parameters and the layers in this particular model. So you can see that just by printing this, we have an overview of what it looks like. And moreover, just by calling named parameters on the model, we can actually iterate through each and every single parameter in the model. So you can see that for each layer, this gives us the weight matrices, the biases, and so on. Let me just scroll down. And just to show you a little bit more of how to take a look inside the models to see what we have seen already before, if I look at the third layer, which is the output layer, and I look at the weight matrix, the shape of that weight matrix is 10 for 10 times 150, because 10 is the number of output layers and 150 is the number of inputs coming from the previous layer. Okay, so now we've got everything we need to do the forward pass. As we said already, in a multi-class classification problem, each and every of these 10 neurons is going to output values that we typically call logits. And these logits, if we pass them through a softmax activation function, they will actually give us the probability that the input belongs to one of the discrete classes that we're looking for. Now, before we can pass our tensor image into the network, we have to reshape it. This is quite important to understand. If you remember, the input to a layer of the neural network is essentially shaped so that the first dimension is the size of the batch and the second dimension is the actual input features. So for this one, we have to take the 28 by 28 matrix and we have to add a batch dimension. So first of all, we have to add a batch dimension, which is this one here, obviously one item in the batch, but also we have to take the matrix, which is 28 by 28, and flatten it. That's important. So that's what this is doing for us. And you will see that now everything is flattened. And if you count the number of brackets, you will see that we've actually added a dimension there for the batch. So we've got this, and we can now pass this through our model. That computes the forward pass, and we can take a look at the output. Incidentally, the output is often called y hat for that. So if we look at that, obviously we have a tensor with 10 values in there, which represent kind of the probability. Well, these are still the logits, but if we pass them through the softmax function across the first dimension, we actually get the probability that the input belongs to any of the classes. Now, in this particular case, obviously, I think this is telling us that this number is the number 7, because that's the highest value. In practice, obviously, this is just initialized with random weights, and this is not the number 7. What we're going to do in the next videos is seeing how we can train this network so that it actually outputs something sensible. Before finishing, I wanted to quickly touch upon GPUs. We saw how GPUs can perform these matrix operations very quickly, and PyTorch is geared towards working with GPUs seamlessly. So in order to do what we did but on a GPU, first of all, we simply use PyTorch to check whether a GPU is available. And in our case, no GPU is available. So we can go to this notebook and we can change the runtime so that we use a GPU. Notice that changing the runtime is gonna restart the environment and you're gonna lose everything. So we're gonna redo the entire notebook from scratch. And that's very simple because we can say run before, and it's gonna run all the cells before. It's gonna re-download all of the MNIST dataset and process it as we did. It shouldn't take long. This is quite small. But now, after we get here, the device detected should be CUDA, which means that PyTorch has detected we have a GPU and we saved that we have a GPU in this variable. Now we can take the model and we can simply put it to the device. So that transfers all the weights and the biases to the device, and then we can perform the forward pass as before. And this should return an error. Let's give it a second. The reason why it returns an error is because now the model is on the GPU, but the input that we're passing to the model, which is yet another matrix, is not on the GPU. And that is telling you exactly that. So it's important when working with GPUs that we are indeed putting everything on the same device, so you're going to get these errors. Now, by fixing this, we did the forward pass correctly, but this time on the GPU. And if we look at these, we now see the output of the 10 classes again. And you can see that the device is CUDA. Well, this was all for this coding lab. I'll see you next time to discuss how we can actually train this neural network.